The last topic is technical given by Tudor Giurgica-Tiron, and the title is
Great, thank you, Tommy. In this talk, I'll be presenting my recent work, joined with Bouland and Stanford, in which we revisit the well-known Solovay-Kitaev theorem. We were able to remove the requirement on inverses. So, to begin, it's worth remembering why Solovay-Kitaev stands alone to be a theorem on the whole theory requirement. The short is because it connects the notion of universality to the idea of conditions. And here we're really going back to foundational material, which is a private place in classic textbooks. So universality is primarily about possibility of approximation. So a gate set, you have a finite number of elements. It's called universal, and hence generate all unitary elements. So for a given unitary, and precision approximations, we can find a number of these gates such that when multiplied together, it comes within a precision to the target unit. So we're interested in the precision of this procedure, namely how fast does this length grow with decreasing interval. So naively, we might guess that the scaling is polynomial. And Solovay-Kitaev gives us a very optimistic result that guarantees that actually the space is covered in QIP class, and the length only grows logarithmically with inverse precision. So this is a very big deal, because if you're going to an algorithm, a QIP algorithm that has a polynomial scale, on paper, when you compile it into a specific data set, you only incur one logarithmic cost. So compilation is cheap and polynomial scale up to the day. So we have the freedom of thinking about algorithms without worrying about specific hardware limitations. But there's a visible caveat, this inverse closure requirement. So the standard way in which the theorem is phrased needs an exact inverse for every element in the set. So this, of course, means that for every sequence of these gates, we can take a negative exact inverse. Now, this turned out to be mathematically very convenient, but it's been a long-standing open question to really remove this entire field of application. Let's take a brief incomplete tour through the history of this result. In 1995, Russian mathematician Albert Solovay announces a version of this result over many years, but does not publish it. In 1997, across the ocean, Solovay-Kitaev independently discovers and publishes the result in Russian Mathematical Survey. And to this day, it's the highest rated work of the journal. In 2000, Robert Solovay gives a talk on the result at Berkeley, at MSRI. And he remarks that, to my great sorrow, I have to use the inverses. So there he is, and just as he's about to comment on the inverse issue, it seems, the lecture is interrupted by a fire alarm. Now, you might be familiar with a different line of research, starting roughly around 2012 and still going on today, that achieves maximally efficient compilation, namely logarithm in the first power, for specific data sets, taking advantage of the structure of the data sets. We'll see. This is not going to start this work, but it's worth mentioning as the most efficient known method for compilation practice. Now, the first step towards removing the inverses came in 2016 in the work of Solovay-Kitaev, and Bouland. They were inspired by problems in quantum control and NMR physics. So they showed how an exact implementation of the Pauli group can be used to reduce approximate inverses. And they noticed how this can be useful in the inverse Solovay-Kitaev version. And in 2017, Bouland and Olsos extend this result and formulate a new theoretic language. Right? So really, these two papers are very upstream of the current work. And introduce a lot of the tools that we'll be using as well. Right? And at this point, there's an intermediate version of Solovay-Kitaev that says you don't need exact inverses for everything, but you need some exact structure in the form of an exact error of some finite group, or one design for the same problem. Finally, a strong encouragement came in 2020 from this work by Osmani, Savitsky, and Hradetsky, which was presented at QIP last year. So they prove a non-constructive inverse Solovay-Kitaev. And their work is based on previous results from pure math, so working from the calendar, Bouland as well, that deals with random walks on contact groups. So they show that sequences exist, but they don't tell us not. So in this work, we're able to strike out this condition of inverses, and really we're able to remove any need for exact structure and perfect universality. And furthermore, the algorithm for finding sufficient sequences is itself efficient as a polylogarithm. So to be able to do this, we need to find ways to do the work that the exact structure was doing for us before, while only using epsilon imperfect components. And so the recurring theme will be that we'll take epsilon approximations to ideal components, and we'll have to multiply them in a way to reach something that higher precision than epsilon. And we'll build such an inverse factory that will build approximate inverses that will be precise enough to be plotted where the exact inverses are expected. And construction relies on the representation theory of the Pauli property dimensions. And the key construction is what we'll call a Solovay-Kitaev sequence. So it will be a way to multiply together approximate generators x and z, such that we regain the identity to quadratic. So a better precision to the work start. First, let's review some basic facts about Solovay-Kitaev, how it works from a very high level. Now, the task of compilation is really a statement about epsilon s. Right? So the answer to a compilation problem, at a certain point of the unitary group, is a nearby member of this epsilon gamut that covers the whole unitary. And Solovay-Kitaev works recursively by taking elements from the current net and building a factor net to a resolution epsilon equal to resolution quadratic epsilon. So this means that the precision epsilon resolution of the epsilon net increases up exponentially with steps. While at every step you take a constant number of elements from the current. So this means that length increases only exponentially. So double exponentially plus exponentially is the key to the efficiency. Now, without any loss of generality, I can restrict this to a statement about epsilon s in the vicinity of the identity on the unitary group. And there, I can take advantage of the Lie algebra of this judgment. So the key construction here is something called the group commutator. So the group commutator of two unitaries V and W is simply defined as V times W times V inverse times W inverse. Now, when I'm close to the identity, I can express these unitaries as exponentials in small matrices. And I can do a physicist's favorite trick, which is a perturbative expansion of a BCH type. And the key fact here is that the first order term vanishes. Right? So because as you can see, every operator goes with this inverse, the leading order in A and B, first order term is 0, leading term is quadratic, and this is the key to the Solovay-Kitaev recursion. Now, it's not important to know how this thing attaches to an algorithm. I just want to show you this because this is where the power of the inverse appears. Because even though I place the W, elements drawn on the epsilon net, I can still take exact inverses and this cancellation happens. So it's exactly the power of engineering these cancellations that we have to look for. And the only other fact I want to mention here is that we need to start a recursion somewhere. So it will be an initial epsilon 0 net. Usually the resolution needed for that, the true convergence, is no worse than inverse quantum dimension of space. And this is really the only place where universality is applied. So you assemble this initial net from the gate set by virtual universality, and after that, you never mention the specific case of that. So notice how Solovay-Kitaev is really a statement about the computational theory of the special unitary. Great. So how do we remove the need for exact structure entirely? So the rules are that we can obtain epsilon approximations in the various of our choice, and we can multiply them. That's about it. So can we engineer anything better than a precision epsilon? So the constructions that will generalize some constructions using this previous work, we feel like deserve a special name and we call it self-greatness. What do we mean by that? Consider ideal operators, G1 through GK, in a set of epsilon approximate versions of these operators, so G1 prime and GK prime. So every approximation to an ideal operator should be no further than epsilon, not greater. So subcurrent sequence is a word of these approximate operators, which itself approximates the identity to a higher order of epsilon. Right? In other words, I have an order of multiplying these G elements, such that the ideal result is identity. When I replace these with approximations, I'm guaranteed to also get identity to a high degree of precision. So the result that we show is that such sequences exist to quadratic precision in all dimensions of 2 or higher. So we build the sequences explicitly using approximations to the Pauli generators x and z. In d dimensions, these become so-called Lie operators. So x becomes a shift by 1, and z becomes a phase or clock operator. You can think of these also as shifts in momentum or position on d positions along the circle, for example. So here's the first example. In 2 dimensions, X prime is the approximate X operator, Z prime is the approximate C operator. Here's a way to multiply them to get an identity to the order, right? Using 4 copies of each. Here's an example in 3 dimensions. So I have the approximate exponents of them. I use 9 copies of each. And in general, I have this recipe for this family of instructions that works in arithmetic functions, and we use these square copies of each. So you must feel like I pulled this out of that, and I'd like to explain a bit about that. So the first thing to talk about really is what's so special about the special individual? Like where does the special property come? And the answer is that it comes in the structure of the error. So really, without going into too much detail, we'll notice that when we have the approximate Pauli, there are these 2 dimensions. As an interpretive example, if I have the approximate Pauli x as x prime, it's 0 order x to x, then it's going to be a first order error. The first order error will be orthogonal ones, right? So it will contain components along identity, y and c, but not components along x. Those will all be organic orders in that. And similarly for z, the approximate z will not contain any component along c as leading order. That means the right picture to draw here is a simple tangent space picture. So if you're on top of a hill with true x, and you take exponential steps away, you lose altitude for organic errors. So in other words, the special integrator confines us to this type of concept. This is the structure of the errors. And I could stop here and tell you that once you notice this, you can go to the recipe that I provided, the sum multiplying specificity, and provide proof by the first calculation. Now, that's not particularly insightful. So what's really going on here from a good theoretic perspective? So the claim is that the mechanism is a double group work in which the leading order in the 2 Paulis project out their mutual orthogonal errors. So that's a little mouthful, but let me present. Let's say the situation in D dimensions in which x and z will have order equal to the dimension. And these are degenerative groups, they will generate equal group. And notice how I'm not telling you what the commutation relation is because it will not have explicitly. And let's think about a slightly simpler problem in which one of the operators, say c, is perfect, and x is imperfect. Can I construct an analogous sequence here? And the answer is yes, it happens in 2 steps. And each step corresponds to one of the 2 key subgroups, right? Generated by x and generated by c. So you remember the candidate sequences I showed you, there were all these sort of operators raised at various colors. What happens here? So consider this construction here. And I'm not showing you this algebra because I'd like you to follow it line by line, but because I want to emphasize elementary. So raise this imperfect x to the power of the dimension and look at the first order term in the error. So if you squint your eyes, you notice how this way we do from the different order. Right? So the observation here is that this is actually a group average, also known as a group world. So group average or group world is precisely this instead of a sum. It's some of these conjugation sandwiches of an operator and an element of the group on the right, on the left, and inverse of the group element on the right. As you might be familiar with constructions from other areas such as benchmarking or the theory of nuclear designs, you haven't seen these sorts, it's all right. The only fact you need to know is that this acts as a projection. So the group average of an operator projects the operator onto the space which commutes with all the elements of the group. So if this was an era, it would project onto the identity because that's the only direction which commutes with all the elements of the group. And that was the trick that was essentially relying on some of the previous intermediate. Here, this representation is very much reducible as a representation of C1E. And the space which commutes with these elements is the powers of x itself, right? Instead of powers of x. So once I do this step, I only project out all other directions apart from the powers of x. So I'm left with a pair which only contains powers of x. And I have to do a similar trick to get rid of the remaining directions using the exact z that I have access to. So again, the algebra follows in a singular elementary way. The structure looks like C alternating with the result of step 1. When we do this t times, the expansion is exactly like a group average of the remaining error of step 1 against the elements of the subgroup generated by C. And because those were among powers of x, they do not commute with any of these. And so I get 0 at the order, which is exactly what I want. So you might ask yourself, why don't you identity? Right? Because that commutes with everything. Well, that's taken care of by the special property that we just seen before. Great, fantastic. So what have we done so far? We've fixed this imperfect x prime with a perfect z, with this double group average hidden perpetually within this simplification. So by symmetry, by exchanging symmetry in the various labels, a similar sequences fixes the perfect c with the perfect x to be written in the following form. So these are all simpler problems than the full problem I've solved. Right? I want a sequence in x prime and c prime that performs the same function, and that should contain these two subproblems as subproblems. Right? So the claim is that if I find such a master sequence, so a sequence of x prime and c prime, I look at its expansion. Right? So I have a zero order term, which should be the identity. I'll have a number of terms involving the area c first order, a number of terms involving the area s first order, and the right. I want the correct terms to collapse down to one of the sequences in the appropriate cases. And so when x is perfect, delta x is 0, right? So that third term doesn't matter. The first two should look like the sequence. Similarly, z is perfect, the sequence whereas the third term belongs to the main sequence. And the claim is that the candidate sequence I provided performs exactly that. Right, so it doesn't need to follow the algebra again. I'm just trying to emphasize the dimension aspect of this construction, but you can just look and see how when I take x prime to x, the powers of x to the power of t are really identical. The whole first half of the sequence passes down. So now this construction is by no means unique, but with this type of insight, it becomes more of an exercise in combinatorics works over the three-dimensional model. So we're essentially almost done. The only thing left is to show you how this construction can do inverses. So what do I do in the recursive step of the algorithm? I'll ask for an approximate x, an approximate z, and an approximate inverse to the unitary u I'd like to invert. To the approximate inverse to the sigma phi, the first element. And I can build an equivalent sequence that approximates the identity by bootstrapping off of this x prime c prime construction that we've just seen. And so if I have a construction involving x prime and c prime for this function, I can find a second version of x prime by multiplying x prime with this object disclosed by identity, right? Made of the approximate inverse of u times u. So I will obtain a whole sequence based on the same pattern of x prime c prime, which approximates the identity of quadratic order, and which conveniently ends on an instance of u. Right? So if I peel off the last instance of u, everything coming before that functions exactly as a quadratic precise inverse of u. And this is the inverse method. Right? A similar trick was used to assume this word from these objectives. And again, this is quadratically precise inverse. It's good enough to plug, it's Solovay-Kitaev, and the result follows. So there's a cost to pay for this in the construction itself. So there are these squared elements in the proof, and really implicitly in these sequences, all elements of the proof are being visited from another way. So we'll have already squared length approximation sequence at every step of the algorithm. And this is reflected in the exponent. So the resulting exponent, the only log by asymptotic, will scale logarithmically dimension. Right, so finally, let's look at the consequences. So this naturally extends to the special linear group. So already, our Ronald and Klaas took the inverse full case to the special linear group, and now we have a way to provide the same construction. So this we get. And the main application of this result will be in complexity theory. So there's all kinds of constructions involving gadgets, and we'd like to prove how powerful these gadgets are. So there's no guarantee that these gadgets will be inverse closed. And there's a lot of work in that sort of avoiding, right? Streamline the whole series of constructions and post QIP and conflict complexity as well. This is the perfect audience to ask that how would you do it? Have you ever encountered a situation where such a result would have made your life easier? And we hope that some of these constructions could be practically useful or where else have this non-dynamic public and also some. So if errors are coherent, you could use some of these constructions. There's certainly a level of problems left, but we still have to reduce the exponent from logarithmic in dimension to the known non-constructive upper bound of the constant 3. Now, these objects, the so-called self-correcting sequences, seem pretty interesting mathematically in their own right, and we'd like to discuss them. And certainly, from a pure math perspective, it seems interesting to try to extend this to less trivial B groups. So even extending it to special orthogonal groups seems to require some new ideas. So there's a lot of work to be done, and we'll end here. Thank you.
Like numeric suggest that say you ask if reduce the exponent numerically suggested you can let in space.
So the upper bound of 3 comes from the work from 2020 by one makes listing or density, and they use these kind of sophisticated probabilistic methods coming from pre-method literature, and they show an about the 3, non-constructive. So we know that should be better. Yes, the question, I apologize. The question was whether we have numerics that show that it should be easy to lower the exponent.
Hi, thank you, Tudor. Maybe people weren't too concerned about this inverse free assumption because the gate sets that they use are universal and they are inverse closed. So, can you give an example of a universal gate set that's not?
Sure. Well, I mean, just mathematically speaking, I assume the set of gates which are inverse closed will be measure 0 across the gates. So I like to sometimes begin the clocks if I have more time with maybe an animation like this, which is played. But usually there's an animation I have to show about how the block sphere is filled with rotations across 2 random distances. So even that, for example, to have 2 random rotations with block sphere was not known to provide additional calculation before. And so if you look at some of these pure method literature, it's usually phrased in terms of big random elements and show that it's actually fills up the space.
Right, thank you.
Thank you.
The question about the exponent for SU2, we have what's the big of in front of the ball.
Great, yeah, great question. So what exactly is the exponent? So yeah, the question is, what is the exponent of dimensions?
Yeah.
So the inverse full case, in the classic case, we have a present exponent of the say no more than 4. And then we can go up close to 3. Our exponent, yes, it is larger. I think it's around 6.